This learning video covers two topics, earthquake damage and earthquake predictions. So we all know that ground shaking is a common phenomenon that occurs when there's earthquakes. But what other earthquake hazards are there? Liquefaction of the ground occurs when buildings are built on soft sediment that are loose, and the groundwater, because of the shaking, can surround every single grain of this loose sediment and turn it into quicksand. There are two short videos in Chapter 9 that demonstrate how liquefaction takes place and also gives you an example of liquefaction from an earthquake in Japan. Make sure you take a look at those. So when liquefaction occurs, buildings just sink. Here's a building that sank in a Mexico City earthquake in 1985. It just rotated off its foundation and sank into the ground. Sometimes the pressure in the ground actually shoots the sediment to the surface, and we get these little volcanoes. Here's an extreme example of liquefaction that occurred in Japan, and these buildings look like dominoes that just fell over and just sunk into the sediment below them. Another hazard includes tsunamis or seismic sea waves. This occurs when an earthquake happens out in the ocean, and if you think about the ground of the ocean moving like this suddenly, well then all that water above it also moves and you get a ripple. But this is a ripple of a great proportion. You'll notice that the speeds are very fast out in the open ocean. They slow down as they get to the coastline because there's a drag. The interaction of the waves and the seafloor start to make those waves go up because they have nowhere else to go, and that's when the waves really get tall, when they hit the coast. Here's a computer simulation of an earthquake occurring in the Aleutian Islands and the waves that would be generated. It would take about 4.5 hours for this tsunami to get to Hawaii. Hawaii is actually in a bad place when it comes to tsunamis because there are subduction-related earthquakes all around the Pacific Ocean, and those are often underwater. So these are some travel times for how long it would take various tsunamis to get to Hawaii. And again, we don't always know the tsunami's coming in deep water. Here's a picture of some person who I don't think we ever found again in Hilo, Hawaii. And when this great tsunami occurred, they finally decided to establish the tsunami warning system in Hawaii. Another well-known tsunami event was in 2004, the Indian Ocean tsunami. This event killed almost 250,000 people. And unfortunately, the tsunami warning systems that we have in the Pacific Ocean were not available in the Indian Ocean at the time, so no one even knew a tsunami was coming. As you can see here, when a tsunami occurs, the leading edge actually pulls the water out to sea, and then in comes the first giant wave. So people, like shown here, often go out and say, oh look, the water receded. And then of course, the water turns around and comes back. So this was in the Indian Ocean, and if you look, that picture is actually a close-up of this picture right here, and all of these people apparently did survive this tsunami. The epicenter was located near Sumatra, and we're actually going to do a lab on this particular earthquake and on the tsunami. Here's a large subduction zone, which is the cause of the earthquake. And here's a picture showing the tsunami waves over a certain amount of time. Places like Banda Aceh, Sumatra were totally devastated. This is before the tsunami, and this is after. This is what was left behind. It was an incredible disaster. Another big tsunami that occurred was in 2011 in Japan. This was a magnitude 9 earthquake, and I should mention that the previous earthquake was a 9.2. This struck offshore, and then the tsunami began to arrive 10 minutes later. Here's a picture of that tsunami moving into Japan's coastline. Notice that it's not like a large, giant tidal wave that they have in cartoons. It's a huge wall of water that moves towards the coastline. Here's that wall of water moving over the coast, and this is the same event that produced explosions at the nuclear power plant in Japan. Other hazards include landslides and collapse of the ground. These landslides in Kashmir were caused by an earthquake. Here's another example of a landslide that was caused by an earthquake. The largest earthquake ever recorded in North America occurred in Alaska in 1964, and this is one of the areas of damage. there was a little town called Turnagain Heights, and it was built on layers of sand and gravel. And then at some point below the surface, there was a layer of clay. Now, if you know anything about clay, if you pour water on clay, it's not going to go through the clay. The clay is water resistant. So what happened was the shaking from the earthquake caused all these cracks. Water got in, and the entire region above the clay layer slid 200 meters, that's almost 2 football fields, into the Pacific Ocean. I'll show you a picture from this area right here. And it's almost hard to tell which way is up, but I'm pretty sure the camera is in the right position where up is at the top of the photo. And these stairs are pretty much in the position where they might have originally been. The rest of this slumped downwards. And this is what it looked like from the air. This is the whole region that slid into the ocean. Fires are also a hazard when it comes to earthquakes. This is the fire at the Fukushima power plant in Japan from the 2011 earthquake. Here's a fire that was generated by broken gas mains in the Northridge earthquake. Finally, lines of communication and emergency equipment can be damaged and make it very difficult to get assistance to people who need it. What about the buildings themselves? Well, earthquake destruction is really dependent on several different things. First of all, the intensity of the earthquake, how close are you to the epicenter? The duration of the vibrations. The earthquake in Alaska in 1964 was said to last 3 minutes. The main shock, 3 minutes. That's an enormous amount of shaking. The nature of the material upon which structures are built is very important. And the design of the structure. We've learned in California that there are certain designs that withhold shaking a lot better than others. Here's some of the damage from the Alaskan earthquake. Here's some building damage showing a former J.C. Penney's that was pretty much demolished next to this building, which has lots of glass in it that didn't seem to fail at all. Here's a hotel that collapsed in a particular floor during the Mexico City earthquake of 1985, and another type of collapse. So the 4 kinds of engineering designs that are of concern include pancaking of floors, like this, where the walls are weak and it pancakes. This is especially common in parking garages that don't have a lot of wall support. Here's a bridge that was designed to be efficient, but when the earthquake shaking started, it toppled over, and that's actually shown right here. This is in Japan. Bridge supports can be crushed if they're not reinforced properly. And finally, masonry or brick is the worst thing you could use as a building material when it comes to earthquakes. Bricks have no ability to stand the energy that earthquakes send, and they just shatter. We have come up with some new techniques to try to make buildings stronger. And then, of course, educating the public is also very important. Okay, moving on to predictions. We really can't make any short-term predictions reliably. The only thing we can do is make long-range forecasts. And we even did a lab about this, so you're familiar with how we can make these predictions. We have to assume that earthquakes are somewhat repetitive on a given fault and that the probability can be calculated. So here's a map showing hazards throughout the world, and the high hazards are in pink, the low hazards are in white. And you can see that in the US, we are really a hot spot out here by the San Andreas. Alaska is a place where we have a lot of earthquakes. Hawaii is, but only because there's active volcanoes there. So here's a prediction model that was made in the mid-80s to predict the likelihood of a large earthquake on the San Andreas Fault in a 30-year window. Now, of course, this is already in the past, but this is the main trace of the San Andreas, and these were the percentages that were given for the likelihood of a major earthquake. The only one that's actually occurred is the 1989 Loma Prieta earthquake in this area, so that 30% goes back down. These out here in the southern San Andreas have not yet occurred, so all of these percentages are higher now. But let me talk about Parkfield. This one did happen. 90% likelihood. The reason that the authors of this study said that Parkfield was so likely to go is that Parkfield was a part of the San Andreas that seems to go every 30 or 40 years with a magnitude 6. It's unlike the rest of the fault that has long time periods between its earthquakes. Have you been to Parkfield? It's pretty remote, but it is the earthquake capital of the world. Be here when it happens. They're proud of it. So here's the little hamlet of Parkfield, and this road leading into it with a bridge crosses the San Andreas Fault. And in fact, if you're standing on this bridge right here and looking across, somebody put a sign, "Now entering the Pacific Plate." Good geology humor. So here's the history of earthquakes in Parkfield. There was a large earthquake in 1857 that ruptured a large part of the San Andreas Fault, including Parkfield. But then the rest of these are all events, there's time along the bottom, that occurred every 30 years roughly. And here's the magnitude. So the next one that was supposed to occur was going to be in 1987. And if you recall, the window of this prediction model was 88 to 18. So likelihood very high. So this became one of the most highly monitored faults in the world, because if you want to try to figure out anything that might be a precursor to an earthquake, you want to put your instrument where you're expecting an earthquake. So unfortunately, it took a lot longer than a few years. And the earthquake finally occurred in 2004. It was a magnitude 6. It occurred exactly where it was supposed to, and everybody got their readings for their instruments. Today we have this updated map that you've seen before that gives probabilities along the whole state of various magnitudes, and this one indicates various faults that have a likelihood of moving. And the South San Andreas is the one with the highest probability of having a magnitude 6.7. The bottom line is we really can't make short-term predictions. We have to use long-term predictions with probabilities, and that's really the best we can do. Coming up next, earthquakes and how they tell us about Earth's interior.